Okay. I would like to talk about three types of enzyme inhibitors here. So in class, you learn about competitive inhibitor, non-competitive inhibitor, and uncompetitive inhibitor. And you have three types of library graph too. So each inhibitor have different pattern of the graph. So it's your job to understand why it's happened like that and understand what would be the effect on the value of Km and Vmax in each type of inhibitors. So first of all, I would like to use this reaction here to explain about what is a principal lining underlies here. So you have enzyme and substrate, and next it will bind to each other to create the enzyme substrate complex, and then it would breaking down into the product and substrate. So the first part of the reaction, when you have the enzyme substrate complex being formed, so this green box here would refer to the value of Km because it tell you how strong the enzyme and substrate complex can form and tell you the ability to form the enzyme substrate complex, correct? So the later red box, the later part of the reaction here, when you have the enzyme substrate complex breaking down into the product, it would refer back to Vmax value. So it's actually the ability to form the product. So in each type of inhibitor, they bind to different sites of the component in the assay. So it would affect Km and Vmax differently. So to begin with, first, the competitive inhibitor. Competitive inhibitor would bind to the enzyme active site. So, and compete with your substrate, correct? So it's bind at the enzyme active site. Thus, it's compete with your substrate. Correct? It's bind at the enzyme active site on the free enzyme. So if you look at this situation, what will happen here is that it would pull the equilibrium to the left. So that's what means your ES complex is gonna be less, correct? So it would be more difficult to form the ES complex here. So competitive inhibitor would change the Km. It would change the Km. So it will increase the Km, right? So increasing the Kms tell you enzyme substrate complex is difficult to form, and there's a higher dissociation rate and low affinity for substrate to bind with your enzyme. So for the graph, you would expect that the value of 1 minus 1 over km would lower, right? Because it's already converted here. But this comparative inhibitor will not affect the Vmax because it's only affect only the Km. So the Vmax will be equal to the initial Vmax. So Vmax apparent would still stay the same. So the graph would look like this when you have the inhibitor. So Km value would be increased, but for minus 1 over Km, it will be less negative over here. Correct? So that is the comparative inhibitor. So next we have uncompetitive inhibitors. So uncompetitive inhibitors, where does it bind? So it's bind to the enzyme substrate complex, and it will only bind after the substrate is bound to the enzyme. It cannot bind the free enzyme, correct? So it will form enzyme substrate inhibitor complex that look like this. And so if you look at this reaction, you can see that from uncompetitive inhibitor bind with the enzyme substrate complex, it would pull the equilibrium to the right. So that means that enzyme substrate complex is forming easily because the inhibitor would like to bind to enzyme substrate complex, so it will induce the formation of enzyme substrate complex. So it will change the Km, and this will decrease the Km value. So if you plot the graph, the value of 1 minus Km up here would be more negatively valued here because the Km just reduced, right? And if you look at the later part of the reaction to see the Vmax, if it's affected or not. So because the inhibitor will also pull the equilibrium to the left side because it would like to bind the enzyme substrate complex. So it means that your product will be less produced from the enzyme substrate complex. So that's why we say is decrease the Vmax. So the graph in the Lagrange plot, you will get the parallel line to the status when you don't have the inhibitor. So Km is reduced, but Vmax is increased. Vmax is also reduced, right? So you get the parallel line here. So the last inhibitor is the non-competitive inhibitor. So where does it bind? So non-competitive inhibitor is also bind at the enzyme, but it can either bind to the free enzyme or either bind to the enzyme substrate complex. And this is not the active site of the enzyme, it's another site, so it doesn't compete with your substrate. Your substrate can still bind to the enzyme, correct? So what happened with the Km? you will see that this is kind of like circle things up here, right? So the Km would not actually change. So Km would still the same. It will not change the Km because your substrate can still bind to your enzyme at the same rate. Your inhibitor doesn't compete with the binding. So the affinity between the enzyme and substrate is still the same, correct? But what happened with the Vmax is that the product would not be produced at the same rate anymore because the enzyme substrate complex is keeping in this loop but cannot form the product. So that's why we say that Vmax is decreased. So in the Liebig plot here, you will get the same Km, but lower Vmax. So lower Vmax is mean that 1 over V is increased. So you get this line when you have the inhibitor here. I hope this graph help you understand more about what is being changed in terms of Km value or Vmax value. And by understand the concept of H inhibitor, where do they bind, and the effect on the Vmax and Km from different sites of binding. So you can differentiate each type of inhibitor here. Okay.